Okay, let's start. So welcome everybody. It's really for me a pleasure to welcome you and for this first workshop on graph neural networks for recommendation in search. So of course, I should not convince you of the importance and the recent growth of this topic in recommendation system. See, for instance, the book of RecSys this year was devoted to graph neural networks for recommendation. It's really a good sign. So I hope that it will not, it's the first part, but I hope it will not be the last part. I'm sure there will be numerous following ones in the next years. So the way we will organize this workshop, so got it, sorry, it's blocked on the left.
What's going on?
Okay. First of all, I wanted to thank all the organizers of this workshop. It's very important. So some are coming from Imperial College London, such as Michael, for example, Michael Bronstein. Some from University of Michigan, Jackie and Yutong. One from Delft University, Elvin, and the other ones, Carlos, Stefan, Thibaut, and myself from Naval Labs Europe. So the way we will organize this workshop is an alternating sequence of keynote talks and paper talks. And we will have a break, a long break, which is more or less synchronized to the RecSys global break. And you could attend either the RecSys break on WonderMe or the local GReS, so WonderMe room. And we will communicate you the link of the WonderMe room if you don't have it. Be aware that it's password protected. And okay, you already get it. So the program will be the following. So Chang Wang will start in a few minutes with the first keynote. Then the first accepted paper will be about knowledge graph attention. Will be by colleagues. And the second keynote by Michalis. And then the break. And then we go back to papers, presentation. The first core guy, content-rich graph neural networks by Joo-Yeon Kim. And finally, the last accepted paper, which will be in the healthcare. So it's quite original. Referral prediction healthcare with GNN by Regina Duarte. And last but not least, the last keynote by Andrew Zai from Pintero. So I think, so just as a matter of organization, we suggest to ask your question just after the presentation. During the presentation, you can use the chat of Zoom to ask your question, but we will answer, or the speakers will answer your question the last 5 minutes of the presentation. So Stefan, do you introduce the first keynote speaker?
Yes. So it's my pleasure to introduce Chang Wang. He's a research fellow at NEXT from National University of Singapore. And if you don't know him, he has already a lot of paper on graph neural networks and recommendations, such as NGCF, KGAT, also like GCN. So we are very glad to have him as a keynote for this first workshop. And we are looking forward to his thoughts on the topic of GNNs and recommendation. So Chang, I give you the floor now, and you have 40 minutes, about 40 minutes with the questions, okay?
Okay, thanks for the invitation and the introductions. Hello everyone. I'm Wang Xiang from National University of Singapore. So I will be introducing graph neural networks for recommendation. So this is outline for my talks. First, I will introduce the background about the recommendation system and the GNNs. And then I will introduce GNN suitable for recommendation or not. And I will introduce some recent advance we are researching into And then we will have a little discuss about the GNNs, disadvantages or the potential limitations. Okay, so first go to the overview of the recommendation system. As we all know, we feed some users and in some contextuals into a recommendation engine. And for example, the user's profile can be the interaction history, demographics, and the social relations, or the some contextual informations like the time, weather, kind of things. And then we'd like to let the recommendation engine search or narrow down the item corpus into a into a short list of item of interest. Here, item can be the products, news, movies, videos, friends, kind of things. And as we all know, the key challenge lies in the recommendation system is how to bridge the gap between the user and item features, because the user item features are different type of the entities and are represented by the different features. So we cannot directly introduce the similarity between their raw features. So we borrow power from the deep learning and machine learning, and we cast the recommendation task as a supervised. Sorry for the typo. Supervised learning problem. So the paradigm, the common paradigm is we feed one single. We feed a user item pair or the interaction with some side information, says contextual or other side informations as a one single data instance. We feed this into a recommender model. The first part is to do some representation learning. So we generate representation of the for each input features, and then we based on that input features to do the interaction modeling. We perform the predictions based on the interactions, and then feed the historical interactions to optimize our models. So this is this figure shows a paradigm. So this is our data, and we fit one item, or we fit one user and item pairs into the models, and then do the representation learning to get the user representation, item representation, or the other features. For example, the micro video recommendation or the knowledge graph aware the representations. And then we do the calculate the calculate the probabilities of how user are likely to click the item. So get the YUI delta here. So, but the key problem of this paradigm is that we treat each user item pair as an isolated information item. But the word is more closely connected than we might think. So, for example, we have in the real world we have the user connections. See some social relations or the same or the different people, but in the same demographic groups. Also, we have the similar profiles. And for the user item interactions, we have the different types of the different types of the interactions, like the implicit feedback, explicit feedback, or the sequential patterns. And for the item connections, we may have some knowledge graph things, or have the attributes of the properties. And then we can group the users into the different groups based on their attributes. Also, we can split them based on their multimodal features. So the word is more closely connected than we might think. So how to use such connections to boost or enhance our recommender models is a problem we are interested in. So the first thing is the different rather than formulate them into a isolated or the different item instance, we organize our data into a graph, into a network. And then we apply some graph learning or the graph reasoning technicals to help our representation learning and the interaction modeling. And so graph neural networks are extremely popular and powerful, and it's a powerful tools to get the graph learning, graph representations, and to perform the graph learning and the reasoning. So this is one simple example for the semi-supervised node classifications. So we have the different, we have the nodes, we have the one graph, and some parts of the graph are parts of the nodes are labeled, and the other are not. And then we can do the message parsing to pass the representation or the neural message between the nodes. And then we will get the representations of the different items, different nodes. And then we can build some classifier in the, on the item representations to do the classification. So this is a GNN. So as a basic idea behind the GNN is very simple. It's to do the information propagation. So the average or the aggregate the information from the neighbors and to update the representation of the equal network. And then they built another or additional neural network on the representations to do the classification or to do the predictions. So this is a common paradigm or the common formulation of the GNNs. And this is our target desired representation of the one node's way. And this is a sum, n way is the neighbors of the node's way. So we sum the representation or the embedding of the nodes. And then we apply the neural network to do the feature transformation of the information distillations. So this is a basic idea of the GNNs. So our key problem here is how to transfer the graph neural network or how to apply the graph neural network in our recommendation tasks. And the second question is, are GNNs suitable for the recommendations? Can they boost our performance or not? So here I take the two examples in the two different scenarios. The first one is a collaborative filtering. And the collaborative filtering is the most fundamental task in our domain. So the basic simulation is the similar users would have the similar preference on items. So, when we talk about the collaborative filterings, we talk about the collaborative signals. That is, we would like to capture the behavioral patterns of the users, and then we can treat the behavioral similarity among users as a signal to do the recommendations. So for example, if the U1 and the U3 have interacted with the same items, I1 and I3, so U1 is likely to have the similar preference on other items I4 because I4 is is selected by the U3. So the U1 and U3 will have the behaviorally similar. So with the limitation of the current CF models, here I take the example of the matrix factorization MF. So let's recap our common paradigm of the recommendation models. We split each models in two modules. The first one is to do the representation learning. The second one is to do the interaction modeling. So in the first part, representation learning, MF is simply project the ID of each users and each items into hidden vectors. That's called embeddings. And as for the interaction modeling, it just applies the inner product to calculate the similarity between the two, between the user embeddings and the item embeddings. And the first part for the representation learning only consider the ID informations. and they cannot encode the CF signal explicitly, as they only consider the one data instance or the one user item pairs independently and individually. So we'd like to take care of this problem and to solve this one. So the first thing is to replace the CF with the high order connectivities. So what's the high order connectivity between the user and items? We reorganize the user item interactions, historical data, into a bipartite graph among the user nodes and item nodes. And then we can, when we zoom in the one users, focus on a specific user, say U1, and we can extract a structure, trace structure of the U1. So, and the click, her click items consists of the first order neighbors of the U1, and have the similar interactions. Have the similar histories users will consist of the second order neighbors, and then the paths that reach U1 from any nodes with a path length less L than 1 will be the high order connectivities. Say the I4 to U2 and to I2 to U1. So this path will be the high order, will be the three order connectivities between the I4 and the U1. So this high order connectivities is a natural way to encode the collaborative signals in the interaction graphs. And then the second thing is how to convert these CF signals. How do we encode these CF signals into the representations? Here we borrow those ideas from the GNNs. We do the information propagations. For the information propagations, it can be split in two parts. The first step is the information aggregations. We aggregate the information of the neural message from the neighbors. So here is for example, we care about the U, and then we treat we'd like to get the message parsed from the item I to the U. And then we target the item, the neighbors item I, and then we use a neural network, a simple MLP, to get the neural message depend on these items. The W2, this W1 and the W2 is the neural network, and the EI is the embedding. EI and U1 are the embeddings of the item I and the user U. And then, as through these transformations, we can distill the useful information from the neighbor I. And then the second is to do the representation update. And then here we aggregate or combine all the messages or all the informations from the neighbors into by a sum of the sum pooling or the average pooling. And then this MUU is a self connection between the user between the item U. And then we throw a leaky ReLU to distill the abstract information or to get the more abstract representations. As such, through this way, we can stack the multiple layers, multiple convolutional layers, and through this way, we can encode the three type of multiple high order connectivities or the connectivities from the multi-hop neighbors into the single representations. So this is our key idea of the NGCF, and to use the graph neural network to enhance the representation of the CF models. And another work is LifeJason. It's quite simple. It's founded upon the NGCF via the simplified information propagation, because the graph neural network are originally proposed to serve the node classification or the graph classification, And in those original tasks, we have some rich information or the rich pre-existing features about the nodes or the graphs. But for the CF applications, we only have the user ID, item ID, and their interactions. And so in our cases, the item, the user, some non-linear activations or the non-linear transformations are redundant because we already have the rich embeddings or the huge embedding tables for the user and items. So here we delete several redundant components like this one discount factors we remove. And the nonlinear transformation when we discard them, and this nonlinear activation functions. So we only simply combine all the neighbors together. So you can treat or you can view the LifeJason as the enhanced version of the SVD++ or the enhanced version of the FISM. And this is our experiment result to show how the graph neural network help us to achieve the SOTA performance. As we can see, compared with the traditional traditional CF models like the MF as the neural FM or the CNN, and we can achieve the best performance of the two data sets. And this verifies the importance of the capture the CF signal in the embedding functions. And this verifies the powerful of the graph neural network in the CF signal, in the CF scenarios. And the second case I would like to present is in the knowledge-aware recommendations. Because in the CF scenarios, we only have the user, item, and their interactions. And but in these scenarios, we would like to involve the knowledge graph things. We would like to enhance the item external connections. So the knowledge, we can transfer the knowledge graph or using some common sense knowledge from the like the DBpedia or the ConceptNet or the Freebase to extract actual information about the users and items. And it will offer the background knowledge on items, and it will enhance it will offer the rich semantics and the relations between the items. And then we combine the two graphs. The first graph is a user item bipartite interaction graph. And the second graph is the item knowledge graph, or the item real entity graphs into one single graph. Is the collaborative knowledge graph. And then these two graphs, these two subgraphs are complementary to each other. And we can through this way, we can narrow down the search space of the interest items, and we can explore the user interest through the knowledge graph in a reasonable or in the expandable way. So, for example, we can recommend item I2. So item I2 to the user U1 through this parse, U1 to I1, U1 to I1, and I1 to EI. So this is the real entity of the about one sinner, and I1, I2 is about the sounds by this sinner. And through this parse, and we can recommend or connect the item UI and the I2. And here I just a list all the list advantages and the limitations about the current knowledge-aware recommender models. So, for example, supervised learning based is that we treat the item knowledge as a pre-existing feature of the items, and then we can use some generic feature models like the factorization machine or the deep factorization machine or the wide and the deep on this model, on this data. And also we can manually extract the path of the meta path about the user and the items. Or we can simply apply the knowledge graph embedding like the trans R, trans E, or the trans H to extract the user to extract the item feature item knowledge as one item representations, and then we feed the item representations into the recommender models. But they all have the different limitations. So I just skip this one and we'll introduce our work. And our work is about the KGAT, the knowledge graph attention attention recommendation models. Similar to the NGCF. At the core is the information propagations. We aggregate the information from the neighbors. But the key difference here is we apply an additional knowledge-aware attention modules because for one items it can connect to the thousands or hundreds real entities. For example, for a song, and we can have the singers and brothers or the some user clicks or the writers kind of things. And we would like to indicate which relations and which entities are more important than others. So here we apply the knowledge-aware attentions to indicate the importance of the different entities. So for example, we can apply the simple MLPs or the simple neural networks to calculate the attention scores. But the attention score is dependent on the distance of the entities and the tail entities and the hand entities. And then we can get the attentive sum up to the item representations. And this is our experiments result. As we can see, our KGAT outperforms other baselines through the 3 data sets. And besides, we can offer some explanations about why the user, to explain why the user are interested in these items, or why the items are suitable for the users, for the target user. So, for example, we can highlight or the visualize the attention scores of the collaborative knowledge graph, and then we can extract the paths with the with the highest values or the highest attentions as the explanations. And next, I will introduce some recent advanced or the what topics we are researching into. So here I list some common issues in the recommendations. As we all know, one of the most challenging issue is the sparsity issues. We only have the sparse observations, or the observed interactions are very sparse. For example, the sparsity can be around the 99%. And then the user item interactions presents a skewed data distribution or the low power distributions. That means the high degree items will get the large impact on the representation learnings, and suffering from this skewed data distribution, we will ignore the tail representations in the distribution, and we will get some suboptimal representation for them. And the third issue is noise, because because we care more about the implicit feedback than the explicit feedback. And in the implicit feedback, we will have some noise because we didn't have the ground truth about the user, whether the user are like or whether user like or dislike some items or not. So to serve this, also to serve also magnetize the three limitations, we borrow some ideas from the self-supervised learning. Self-supervised learning as widely used techniques in the computer visions and NLP. For example, the very famous work MOCO and SimCLL, and in the computer visions, and the BERT or the transformer in the NLP. And the basic idea of the self-supervised learning is that they create some pre-test task for the models from the data input data itself. So this actual task is different from the downstream tasks. So for example, if we would like to do some image classifications, and the image classification here is a downstream task, and then we will create some other tasks as the pre-text task, and then we learn some actual supervision signal from the data, and then we pre-train the model on these actual tasks, and then we fine-tune the model on the main task of the interest. So let's focus on the one main branch here is the contrastive learning. So for example, we would like to do the image classification to classify these two images into the dog and the cat classes, and here we can use some image self-discrimination as the pre-task task. So in this task, we need to define or identify the two kinds of the instance. One is a positive instance. It can be the two augmented versions of the same image. And about the negative pair is a two augmented version of the different image. Because, for example, this is our original image. So this is our original image, and we can guess we can rotate this into the different directions, and then we to blue them add some blue filter on these features, and to generate the positive pairs. So so those tools are positive instance. And but the negative things is the cat image here, and the dog image here is for the different argumentations of the different views of the different items. So they are the negative instance, and then we can apply the contrastive learning laws, for example, inference laws, and to maximize the agreements of the positives, because we would like to maximize the agreements of these two images and minimize the agreements of those images. So how to transfer this idea into our recommendation scenarios, especially in the graph scenarios, and we can follow this paradigm to define our graph self-discriminative tasks. So for example, this is original graphs, and we can do some edge dropout or the node dropout, and to generate or to create a subgraph from these original graphs. So those two graphs are the positive pair, and then for another instance, also for another graphs, and those two original graphs are the negative pairs. And then we apply the contrastive learning to maximize the similarity or encourage the similarity between those two, between the repetition of the two positive instance, and minimize the similarity of the repetitions of those two negative pairs. So follow this way, and we propose our models as SGL, the self-supervised graph learning, for the recommendations. And we need to, the first thing is we need to create the different views of the augmented version of the graphs. So here we propose the three methods. It's a node dropout, edge dropout, and the random walk. So the random walk is the layer-wise the node dropout and the edge dropout. And through this way, and we can generate, for example, this is our user item bipartite graph. This is the original graphs. And what we can use the edge dropout, node dropout to get some subgraphs. And for one node here, for one node here, his different views can be viewed as the positive, and for the different views from the different nodes, different users and the different items can be the negative pairs. And upon this augmentation, upon this views, and we can apply the contrastive learning loss, is influence loss, to maximize the agreements of the positive pairs and minimize that of the negative pairs. So this is influence loss. And as we can see, ZU prime and the ZU double prime are the different views of the same user U. And but the ZU prime here and the ZV prime double prime here are the different view of the different users U and user V. And then we can this loss, this objective loss, can be the pre-task task. And for our main task, we remain the supervised loss, BPR loss here. And we can choose the different training strategy to train our models. The first one is we just follow the MOCO or the BERT, and to do the pre-training and then do the fine-tuning. And then the second branch is that we can do the multitask learning. We can change the main loss and the self-supervised loss at the same time to get the representations. And here are our experiment results. As we can see, our SGL models can achieve the significant improvements over the SOTA baselines like the LifeJason or the MultiVAE or the NGCF. And this proves the outstanding performance over the supervised learning task, the self-supervised learning. And then we attribute this success to the outstanding performance on the tail items. Here we split the users into the different groups, and as we can see, our method is the red bars can achieve the significant improvements over the LifeJason. So it means that if we use the self-supervised learning, we can somehow get some actual supervision signals, and then we can generate the high quality representations for the tailed items and the tailed unactive users and the long-tailed items. Okay, so this is what we are researching into, and then is another question is any advantages about the graph neural network based GNN-based recommender models. So recently we found that if we're using the GNNs, and we will enlarge the popularity of the data bias in the data set. For example, the popularity bias. So as the figure on the left shows, this is we split the items into the different groups based on their popularities, and then we expect we can recommend the items only based on the user's interest, and not based on the how popular they are. And but for example, in our experiments, we found that LifeJason is this green line will enlarge the popularity bias than the MF. It means more popular items in the training data will be recommended much more frequently than expected. And a model is pruning to recommend items simply from their popularity rather than the user item matchings. And then this is our another work and another observations. And in the user item feedback loop and the recommender models, especially the GNN-based recommender models, will enlarge the popularity embedding. For example, enlarge the popularity bias. For example, the users, these users would like to see some action movies rather than the romantic movies. And but after one feedback loop, we trained the recommender models, we found that in the new recommendation list, the action movie will dominate this list and compress the space of the romantic movies. So it proves that the GNN models will enlarge the popularity bias. And we attributed this problem to the degree bias in the GNNs.
Just to let you know that you have five minutes.
Okay. Yeah. Thanks. We would like to solve some these issues with the causal inference. And the causal inference is we can do some deconfounding things with the backdoor adjustment or the front door adjustment. Here in the backdoor adjustment is we treat some popularity bias as a confounder between the user reputations and the user preference. In another words, is a popularity bias will be the common cause of the user reputation and the preference, and it will generate the spurious correlation between the user's true interest and the recommenders list. And we have the two papers published in the KDD this year, and to solve these problems. And so this is what we are researching into, and in the I think it is a very interesting also promising directions in our domains. And so let's move on to the conclusions. And thanks to the graph neural networks, and we can leverage the high order connectivities between the user items and other real world entities. And then we can encode the collaborative signals or the knowledge-aware signals into the repetitions. And then we can, thanks to the self-supervised learnings, we can generate the actual supervision signals, and such supervision signals can help us to generate high quality representations for the long tail users and the long tail items. And thanks to the causal inference, and we can serve the data reduce the data sets bias. And but here is some take-home messages. And thank you. That's all my talk. And thank you.
Thanks a lot, Cheng.
Okay.
For your an exciting talk.
Okay, thanks.
Are there questions in the audience?
Yeah.
Yeah, maybe I can start with a question. So thanks a lot, Xiang, for the great talk. I had a question on the robustness of GNN recommendation models to adversarial attacks or noisy data. For example, for a model like LifeJason, there is no filtering mechanism on what should be propagated, given that there is no fully connected layer on the aggregation function. So I'm wondering if this kind of model would be more easily affected by a noisy graph. For example, a graph where you have implicit feedback that can be sometimes inaccurate, for example, with click data, or even a graph with some malicious users that choose items in a random way. So what are your thoughts on that?
Yeah, so great questions. And for the noisy data set, for the noisy implicit feedback or the some noisy data in our graphs, and we can use self-supervised learning, and we also can use recent invariant learning. So the for the invariant learning part is we can treat some noisy data as the environments, because some user preference over the can change or can unstable over across the different environments. That means that due to the noisy data, the user representations, the connections or the correlation between the user actions and the user preference are spurious. So we can split our data set into the different environments, and then we expect some stable or the clean data to stable in the environment across the noise. And for the self-supervised learning part, if we use the edge dropout or the noise or the node dropout, we can manually enhance their robustness across against the noisy and adversarial attacks or the malicious behaviors. So hope my answers can solve your questions.
Yes, thanks a lot.
Okay, thanks.
Okay, there is a question from David in the chat. What are the methods for incorporating contextual information to GNN learning and prediction?
Yeah. So thanks for asking. And here I only introduce these two problems, the collaborative filtering and the knowledge-aware recommendation. But for the contextual things, and I recommend you can search one paper about the GNN. I think it's just published in the CGIAR last year, and it's published in the Alibaba group. And then the key idea is that they can or the dynamic user item interaction graphs, and then we can run the run the GNNs on such graphs to do the representation learnings.
Okay, thanks.
Okay, thanks.
Maybe one last question from Munya Lalmans. How does the quality coverage of knowledge graph impact the results?
The quality of the coverage. Oh, good questions. But in our work, especially in the KGAT, we do the data laundry as do the field. We only keep the items have connected to the knowledge graphs, and we filter some or we remove the items that have no connection to the knowledge graph out. So this is hard to answer because I only based on my research or only based on my experiments. But I think the impact the results. I think it will. It depends, because in some scenarios, I think the CF signals can cover or recovers knowledge-aware informations, and in these ways, knowledge or the knowledge graphs can be redundant. So that means that it's time to rethink to rethink the knowledge, whether the knowledge information is helpful or the helpless. And but in most cases, I think we use the more set information or the more knowledge, and we can get the better performance. That's my answer.
Okay, thanks. So
Thanks.
I think for the interest of time, we will stop the question here. So thank you for all the questions, and thank you again, Qian, for your talk.
Okay.
If
Okay,
people have
thank
more
you.
questions, if people have more questions, I think they can still talk to you during the break, and or maybe in the chat as well. And then
Okay.
we leave the floor for the next paper. Okay.
So
Okay. Thanks.
actually,
Thanks.
Actually, we are planning for a short break, but given that we are running a bit late, I think we'll directly go to the next papers indeed. So yeah, I think Elvin is the one chairing that.
Okay, then. So let's then start with the first paper of the workshop, presented by Mehrnaz Ahmadi and co-authors from NVIDIA. The paper is titled Knowledge Graph Attention for Sequential Recommendations. Is one of the authors here to present?
Yes.
Okay, so yeah, please share your screen and go on whenever you feel.
Sure.
So you have around 20 minutes, including Q&As, and I'll give you a sign around 14 minutes. Is that okay?
Sure. Perfect. Cool. Hello, everyone. I'm Mehrnaz Ahmadi, data scientist at NVIDIA. Today, I'm going to share our work on knowledge graph attention for sequential recommendations. So basically, this is a joint work with Daniel Mohseni Taheri and my previous PhD advisor, Tejatullah Banhula. So let's start it. So we all know, especially in RecSys, we know the advantage of using recommender systems, boosting company revenue from the company perspective, improving user experience for all users and customers. It has a prominent role in service sectors, and it has various applications and very important ones, including personalization, ads, and search. So today, in this work, I'm going to emphasize on two aspects of information that we can leverage in recommender system. So one part, as Xiang mainly focused on that, was the knowledge-aware part, where we use the product site information and embed it into graphs. We can embed this information into graph format, and specifically knowledge graphs. There is a like very recent literature on that. And also, we have the user dynamic interest, which changes over time. Basically, most of platforms have access to the historical interactions, and they can access to this information, how users has interacted with the platform over time. For example, here we have the example of like the sequence of movies that user clicked or watched. Very rich literature for sequential recommendation. We have the most important ones, and the recent ones are Sastrek and Bertborek. And for the knowledge aware, we have the graph attentions, and GAT is one of the important ones. So moving on, we are interested in that how we can leverage this both part of information in our recommendation system in order to build a in order to enhance the performance, right? Because these are the information that most of platforms have access to it. So specifically, in order to state the problem, we have the set of users and our items and the user sequence. in the T timestamp, right? And the goal is specifically next item prediction, predicting which item the user is most likely interested in the next timestamp, which is T+1. So in a nutshell, what usually happens in practice in recommender system is that we have some experienced users like user 1 here, which has longer sequences, and we have other type of users which are fairly new to the platform and have shorter sequences. So we are interested how to leverage the side information of products, which we call them entities, in order to relate these like different types of sequences to each other and leverage the information that we already learned from experienced users into the recommendations for the less experienced one. Specifically, this problem is called cold start, as you are aware. So we want to help to improve this problem. So we start from the knowledge graph module, which is basically tries to embed the first part of information, which is the site information for products, how to embed this information. So as I mentioned, this information, and Sean mentioned in the previous session and keynote, this type of information can be embedded in knowledge graphs, where we have a set of triplets, which has two nodes as head and tail, and the relation, which is the edge that relates them, right? So for example, here we can see like users on the top as nodes, and we have the items set, which are other nodes, and also we have entities which are not users, not nodes, not items, but these are the entities that has the features, right, for the product. So for example, here this entity can be a director for one movie, while it can be actress for another movie. So the person is the entity, and the relation is embedded into the links or edges in the graphs. So in order to learn about the embeddings like elements of such graph, there's a score defined in TransR, which is basically tries to assign a score for each triplet in the graph. In a nutshell, it tries to understand, it assumes that, the assumption is that the head node, which has been projected into the relation space with the link or the edge of relation should has a very close presentation to the tail node. So this assumption should hold for our valid triplets, versus the broken ones, which do not exist in the graph, should have very different scores. So it shouldn't be possible for them to have similar score for the valid triplets, basically. So in order to train the knowledge graph module, we need a loss function to differentiate these two scores for the valid and broken triplets, basically, which is a pairwise ranking loss. So this is basically how we can learn the embedding from the knowledge graph module. And then after that, that we have our embedding layer, we need to embed or to propagate the embedding of the neighbors into each node, right? Because the whole purpose of having graph is that learning some knowledge from neighbors, right? So in order to do that, we have for each node, we have the immediate neighbors, right? And then now we want to propagate this information from neighbors. So basically what we want to do is that like having a weighted representation of neighbors as a representation for the neighbor of like the neighborhood of the node, right? And it totally makes sense to put more attention or weight on closer neighbors, right? Which can be captured by knowledge-aware attention, basically. So this is how we can get the embedding for the neighborhood. And then when we get the embedding for the neighborhood, we need to aggregate this information, right? So to aggregate the information, we have used the by function that has been introduced in KGAT to aggregate the information from the neighbors into each head node, basically, or any node in the graph, right? It captures the summation part and also captures the inner product, which basically propagate more information from the closer neighbors, right? So moving on, we have the last piece, which is, so all that we mentioned up to now was the propagating the information from the immediate neighbors. But in the graph, we can go further and further to even like second order neighbors and higher order neighbors, right? More and more. So as we stack more layers of attention propagation, we can reach to higher order neighbors, right? But for each node, what we end up, we have like different representation learned from each layer, right? So we have the embedding for the node itself, and then we have the propagated information from the immediate neighbor, and then from the second order, and so on, right? So what we do, we just aggregate this information, concatenate this information into one vector as the final representation for that node, which has been learned by the knowledge graph, right? So this is the last piece of the knowledge graph module that we have. Moving on, so our architecture, as I mentioned, has two main modules. The first one that we just covered was knowledge graph attention module. The next one is where we want to leverage the first module in this sequential recommendation, right? So the whole purpose of leveraging the knowledge graph part was improving the sequential recommendation part. So what we do, we use this embedding that we just learned from the knowledge graph into the embedding layer of our sequential recommendation. So it starts from the embedding that we learned from the knowledge graph part, right? For the sequential recommendation, we have used BERT, which I'm pretty sure that most of you are aware of its architecture. So for interest of time, I don't go into details here, which has like the positional embedding at the beginning and then the multi-head self-attention. But after having the like BERT for this part and transformers, what we have is basically what would be our item embedding. The final item embedding would be basically the embedding that we learned from the knowledge graph part and the embedding that we learned from the sequential part, right? So we learned two embedding and we have the summation of both to consider for our final representation for items. For the output layer, basically the purpose is completely evident. We want to pick we want to predict the next item which has the closest closest embedding to the embedding that we learned from the transformer or the last part, right? So basically, it's a softmax function that captures the that predict the closest item to the latest embedding. Yes. Any questions?
I had one question. Can I ask it?
Maybe we can take
sure.
them in the end, I would say. So there are.
The presentation isn't over. Sorry.
Okay.
So maybe first finish.
That would be great. Yeah, I agree. Let's finish up and then get back to the questions, if you agree. So for the BERT part, of course, we need the closed task training approach to mask the spots in the sequence, basically positions in the sequence, and the loss would be basically the negative log likelihood, right? As we have for most of the next item predictions. For the experiment section, we used 3 different data sets, which are coming from different domains. So we have Amazon Book, we have Last.fm, which is basically like a music platform that people listen to music, and we have Yelp, which is like released from the 2018 challenge, Yelp 2018 challenge. So these data sets are different in terms, specifically in terms of their density. So Amazon Book and Yelp has a similar density, but Last.fm is the most dense data set that we have here. So Amazon Book and Yelp are more sparser, and Last.fm is denser data set. And we want to see how our model can perform among these different data sets. We used 3 metrics, heat, NDGC, and MAP. And here are the results that we have. So our model, KT-REC, showed that we got better performance from the other competitive baseline in sequential recommendation, BERT, SASREC, GRU. But this holds for Amazon and Yelp, but we saw that for Last.fm, this doesn't hold. Even BERT doesn't get the best performance. SASREC gets the best performance, and we had a closer look on this to see why it can happen. So what we had more here as an evaluation study is basically, we saw that for the different sequence length in Amazon and Yelp, basically our model is consistently outperforming. But for Last.fm, when we have shorter sequences, basically what happens is that we get better performance for shorter sequence, but as sequences get longer and longer, SASREC takes over. So this can be because of the density of Last.fm. And as we have like longer sequences, basically when our users are more mature in the platform, we can learn their sequence. We can learn their behavior by looking at their sequence. And knowledge graph basically helps us mainly with the cold start problem, where we have like less experienced customers. So the last piece goes into like visualization of the weights. So we can see that our model has like attendance on different positions when we have different heads. And this is the comparison without positional embedding. Of course, then we don't have the focus on the recent items. And we have also a comparison with BERT for rec, which it shows that without the knowledge graph piece, the attention in the sequential recommendation mainly attends around the position of each item, like around the nearby positions, basically, when we don't leverage the knowledge graph part. And lastly, we can see that here, one of the main reasons of leveraging knowledge graph is also having some sort of interpretability. So here we can see that when we leverage knowledge graph in our model comparing to BERT, we can see that for the items that we can see here, more co-occurrence, higher co-occurrence metrics, we have higher attention in the knowledge graph, like in the existing of knowledge graph piece. So this provides us some sort of interpretability thanks to the existence, like leveraging the knowledge graph piece. Lastly, as a summarize, we provide an efficient and robust deep neural network for recommendation system, which leverage the collaborative knowledge graph, and also we leverage the site information to address the cold start problem. And also we had the comparison with other competitive sequential recommendation SOTA. So our paper is available on arXiv, and it will be soon published in Science Discovery. And I think that we might have some time for some questions.
Yes, thank you for the presentation. We actually have time for one quick question.
Yeah,
Okay.
I heard, yeah, like somebody typed in the chat. Like, how does it compare with the transformers for rec library from NVIDIA Merlin?
Yes, so that the transformer for rec is basically more focused on the sequential part, but here we have the knowledge graph on the top. So it's like two different parts. So we have like the knowledge graph module on the top, but we have the comparison with like a more basic sequential recommendation in the literature. So yeah, so as far as I know, like transformer for rec has different options for your sequential recommendation, but it's morely focused on the session-based recommendation, right? Here we have like more general one, which is like we compared with the general sequential recommendation here.
Yeah.
Okay. So for the interest of time, we can take the rest of the questions in the breakout after the next keynote, or you can continue them privately in the chat. So thanks again for the presentation.
Thank you.
We can now move to the second keynote. And it is my great pleasure to welcome here Professor Michalis Vazirianis, who is a professor at École Polytechnique in France and the head of the Data Science and Mining Group. Professor Vazirianis has received his PhD from the University of Athens in Greece and the Master in AI from Heriot-Watt University in Edinburgh. He has several contributions in machine learning, data mining, and graph mining, and that has also been supported by a lot of funds and received many awards. Today, Professor Vazirianis will present some of his recent works on graph neural networks with random walks. And without further ado, I'll pass the floor to Michalis to let us know more about this. So please go ahead.
Thanks a lot for the introduction. It is a pleasure and an honor to be among you. Let me start the presentation and share my screen. Just 1 second. So share screen. I believe this one. Can you see my presentation?
Yes.
Excellent. So thank you very much for this, let's say, interesting program and this new topic that seems to be very interesting. GNNs, recommendations. GNNs are very popular in the last years, and today I'm going to present a topic about explainability. So the idea is that GNNs have been very popular recently in the last years. We see a lot of papers, a lot of applications in different domains, including recommendations, images, documents, time series. But on the other hand, what do GNNs do? They are learning node features by aggregating and combining neighbor information via mostly the message passing mechanism. And they have achieved promising performance in several graph mining tasks. But on the other hand, so far, GNNs have been mostly treated as, I would say, black boxes. And it is not really interpretable what they do. And we don't have, for instance, features like in CNNs for images, where we see that the features that are being learned have some visual interpretation. What would be the equivalent of interpretability in the domain of graphs? So the idea is that mostly recently GNNs are treated as black boxes, and we lack methods and let's say intuitions on how to interpret. Of course, what does it mean to interpret? What we do in other areas is that we interpret decisions by knowing the features of the data. For instance, when we have an image, if it contains a circle or if it contains a face, this is characteristic for the classification, right? So we need to see what does this mean at the level of graphs. Apparently some graph features that are repeated again and again, and they are contributing to the classification, perhaps. In any case, we cannot fully trust GNN models if we cannot explain them at all. So this is kind of motivating what we do. This is work that, I mean, this presentation is mostly based on a paper that we published last year in the NeurIPS conference that has to do with how to extract from in the deep learning process for graphs, how to extract features, graph-based features that are relevant and interpretable being visualized. So graphs are everywhere. Just to put in context everyone, machine learning for graphs boils down to node classification, to node regression, or to link prediction. If we talk about the node or edge level, these are all very important tasks, and they have been, let's say, honored with a lot of publications and a lot of citations in the recent years. But then we have machine learning at the graph level, which means that we would like to predict the classification of a graph. We would like to predict a value that is characteristic for this graph, for instance, the size of the k-core. Also, another issue which is very trendy and very important recently is the evolution of the graph. Can we predict the topology or the state of the graph in the next moments? And then this brings us the question, what a neural network for graphs should be like. Let me try to, let's say, address this issue based on the architecture of MLPs. You remember, apparently, from our background that an MLP is nothing but a mechanism that produces inner products between representations and trainable matrices. For instance, we have the input layer here, where we have the input of an object X, which is like a vector. It is multiplied by a matrix W1 that is compatible. It has 3 rows and 4 columns, and maps this input data into a hidden representation H1 that has dimension 4. It's a vector of 4, let's say, objects. So this is what we see here. The hidden representation is a nonlinear function f on the product of the input data with this matrix. We need to stress again that the matrix is learnable, okay? That is trained via the backpropagation mechanism. Then this hidden representation is transformed by a second learnable matrix W2 into a hidden representation H2 using, of course, another nonlinear function. And in the end, the hidden representation 2 is mapped via an appropriate dimensional matrix W3 into one output that is essentially the decision about the classification of the input data. So this is what MLPs do. On the other hand, in the case of images, we have that the input layer is a two-dimensional structure, which is the image that contains pixels. And we have different matrices that we call filters, W1, W2, for instance, that are being convoluted over the data and produce hidden representations that are relevant to the features of the images. For instance, as I mentioned before, we can think of lines or circles or color patterns that are present. And in that case, these hidden representations are learned by the H1. That is essentially, as you see, continuous convolutions of the data via these matrices that are being learned. And in the end, we convert, we vectorize actually the H1 representation into the lowercase h1 by vectorizing the previous one. And we have another hidden representation that is mapped into a single decision, a single output y. If you recall, the features are learned here at the level of the convolution. Let's see now what would the graph do. In that case, if we do the analogy with the images, for instance, here that we are learning small trainable representations that essentially represent visual features, edges, patterns, etc. What would be the equivalent for the graphs? So in that case, what we imagine of doing is that given graph G as an input, we can think of some hidden graphs, G1, G2, G3, G4, that are being learned, and they are, let's say, representing the most important features inside the data. which means which are the most discriminative subgraphs of the data that lead to the classification of the training set. So assuming that we learn those graphs, G1 to G4, the hidden graphs, we convert them into a hidden layer 1, then we have other trainable matrices that lead us via the message passing mechanism to the decision. So we see, for instance, that H11 is the hidden representation of node 1 of graph G based on its similarity with the hidden graph G1, and so on and so forth. Okay, so this H1 representation, each of them here, where I'm pointing my mouse, it represents the similarity of the input graph to each of the trainable feature graphs. So this is what we perceive should be a representation for graph neural networks, to focus on the concept of graph-based features. So for the moment, we have the message passing neural networks dominating some estimations say more than 90% of the domain of graph neural networks. So what do we have? What is the state of the art? It is that we have an input layer, which is a graph. This is given as input, or it is, let's say, with the trainable matrix W1, we learn the representation of a node I as the sum of the messages that are passed by its neighbors. So by J, we denote the neighbors of node I, including itself. So we sum for all the neighbors of node I this nonlinear function on the inner product between the representation of the neighbors times this matrix W1, a trainable one, and this is exactly the message passing mechanism. And then we do this for another layer, and then the hidden representation of the node is essentially the summation of all the representations of all the nodes of the graph. This is why we have here superscript 4. And then H2 is the hidden representation that is given to the final layer that gives us some decision, which has to do with the classification of the graph. Okay, so this is the well-known message passing mechanism. So we thought, can we do something different? Is message passing the only way to go? So, but there are some issues that we found that, so the idea, or I hope you can still hear me, because I got a message that it is not stable, my internet connection. Can you still hear me?
I can still hear you.
Yes, great. So the idea is that we need, in order to change the architecture and compare the input graphs to some feature graphs, we need to have a function of comparison between the graphs that are differentiable, so that these matrices can be trained via backpropagation. Another issue is that usually the graph comparison functions in terms of kernels are usually expensive to compute. They have high complexity, especially when the number of graphs is high. And of course, somebody would say, why would we search for another model while the message passing framework has proven to be successful in several tasks? So it seems that there was space for improvement. And also there was space to compare graph kernels with GNNs. And also another issue is, can we design, because we said that the graph comparison functions are very expensive to compute, can we design a function that is also efficient, comparison between graphs function that is also efficient but still differentiable? For this reason, we employ the concept of kernels, graph kernels. I hope that most of us are familiar for, let's say, making the presentation self-contained. We included a slide saying that a graph kernel is a function that maps a graph into a vector in a Hilbert space, and thus we convert the graphs into vectors, and thus we can do any vector-based computation like similarity, inner product, etc. And one of the kernels that is by definition differentiable is the random walk kernel that basically counts the matching walks between the two graphs. I will explain in the next few slides what is this product graph. So if we have two graphs, G1 and G2, the direct product graph G is a graph with vertices V1, V2 that come from the two sets of the previous graph. So for instance, V1 comes from G1 and V2 comes from G2. And the edge set is such that it is that there is an edge between two nodes of this graph if there is an edge between the corresponding nodes in the original graph. So what we say here is that there is an edge between V1, V2 and U1, U2 in the product graph if and only if there is an edge between V1 and U1 in the first graph and there's an edge between V2 and U2 in the... So it's like doing parallel walks in the two different graphs. So here is an example of the product graph. So if we have the graphs 1, 2, 3, and 4, 5, 6, 7, so we see, for instance, that if we try to create a node 1, 4, so 1 and 4, you see this node. 1 is from the first graph and 4 is from the second graph. It has an edge to 3, 7, to 3, and 7, because exactly there is an edge between 1 and 3, but there is also an edge between 4 and 7. Okay, so this is how we construct the product graph. And it basically represents parallel walks of length 1 in the two graphs. So the idea is that if two graphs have very similar random walks in parallel, then they are quite similar. And if we want to put it in mathematics, the power P of the adjacency matrix A of a graph G is computing the lengths of length P on the graph, and this one here is the number of walks of length P from vertex I. So the element Aij, which is the element Aij of the adjacency matrix lifted to the power P, it represents the number of walks of length P from vertex I to vertex J. So for this reason, for each P, the P-step random walk kernel between the two graphs, which is the similarity, can be defined as the double sum that we see here, and so this is the adjacency graph lifted to the power 0, 1, 2, 3 P, where P is the maximum walk length. And you see that each of these adjacency matrices is weighted by some real value that can be set. So to put it intuitively, the similarity between two graphs according to the random walk kernel for a maximum length of P is given by this equation, and the common walks of length P can be computed by using this matrix here, which is the adjacency lifted to the power P, as the adjacency matrix of the product graph. It is easy to understand here that this similarity metric, the random walk kernel, is differentiable because it contains only multiplications and summations that make it differentiable. And then based on this design, we are trying to design this new model where we assume a number n of hidden graphs, G1 to Gn, that are going to be learned based on the training. This hidden graph with n vertices represents n almost n square trainable parameters that correspond to the potential edges of these graphs. And the edge weights, we impose non-negative real values via the ReLU function. Okay, so this is design, let's say, decisions. So then those graphs, G1 to Gn, are used in order to compute the similarity between an input graph G. So we assume we have a new graph G, and we want to compare it against its hidden graph GB. And this is based on the formula that we have seen before. Okay. So the idea is that for each matrix, for each input graph G, we build this matrix H that contains essentially the similarity between G and Gi for lengths, for random walk lengths up to J minus 1, and this J parameter goes from 1 to P. So then at some point, this similarity matrix is flattened. We make it one vector, and we give it into a fully connected neural network to produce one output for the graph based on these similarities. Let's see, or let's try to visualize this idea that is a bit complicated as a start, but we try to visualize it here. So the idea is that we have the input graph G, and for instance, we have hidden graphs G1, G2, G3, G4 in pink color, and we are computing the similarity K based on the random walk kernel that I have described before, the similarity between the input graph G and each of the hidden graphs. And this H11 is exactly the vector, or the vector that represents the similarity between the input graph and the hidden graph G1, etc., etc. So this is the basic, let's say, architecture. The idea, and the black node represents the bias in the learning process. The idea is that in this process, we consider only non-attributed graphs, but in reality, we have a lot of attributed graphs because, for instance, in chemoinformatics, the atoms that are the nodes contain chemical properties. In citation networks, the bag of words representations of the papers are the attributes of the node. So the idea is, can the random walk kernel handle attributed nodes or not? So what we do here is that we are designing somehow how to equip the nodes of the hidden graphs with attributes of the same dimensionality. And the idea is that if we consider Z is the matrix that contains those attributes of the hidden graph GB, then if we let's say assuming X are the attributes of the input graph, then this representation ZX transpose is the product between the attributes of the input graph to the attributes of the hidden graphs. Then we vectorize, which means that we concatenate all the rows of this matrix S, so that we make it a vector, and then we modify the kernel in this manner. So the only difference to the previous is that we multiply this element by the similarity between by the inner product between the vectors Si and Sj that correspond to the similarities between the input graph and each of the hidden graphs. So this is the way how to do it. And then what we notice is that this computation is very, very expensive, because we have lifting of a matrix to the power p, etc. So in that case, we are in search for a method to simplify this complexity. And then in that case, we deal with the Kronecker product, because essentially the random walk kernel is about computing Kronecker products. So the Kronecker product, I believe we all know it. It is a product where between matrices A and B, where each node of the first matrix is multiplied by the entire second matrix. And then if A and A prime are the adjacency matrices of the two graphs G and G prime, and AX is the adjacency matrix of their direct product of their Kronecker product GX, then then this is the Kronecker product between the two adjacency matrices, then we define these operations like vectorization, which is simply converting the matrix into one vector, and the inverse operation like splitting a vector into many and making them a matrix again. Now, the properties of the Kronecker product, for instance, this one, the vector of ABC matrices is C transpose Kronecker product A times the vector representation of B. I mean, there are proofs for that. And if we assume this one and the matrix is A vector to the -1 of B and C, then based on this, let's say, property above, we have that this is equivalent to this one. We will use these properties further on so that we can reduce the complexity of the kernel computation. So for kernel, random walk kernel, which means similarity computation for random walks of length 1, to keep it short, this boils down to this representation that is essentially multiplications of matrices. We don't have anymore these complex operations as above. And if we generalize it to the walks until length p, then the computation of the kernel boils down to this one, that is again summations and multiplications, avoiding thus huge cost that was incurred before. Yes, and this is exactly that we propose the complexity. So if KPGGI is the similarity between the two graphs GGI, based on the previous slides, the complexity is this one that we see. So P is the size of the longest walk, N is the size of the input graph, and B are the nodes of the feature graph, and N and M are the size of the input graph. So doing realistic assumptions that P is much smaller than M, which means that the size of the longest walks is much less than the number of edges of the input graph, and the dimensionality of the vertex is also much smaller than the number of the edges of the graph, then the complexity boils down to this very reasonable one. So also to reduce the dimensionality of the vertex attributes, we can also do that. We convert the data X via a one-layer perceptron into one vector, or even using a message passing neural network, converting the data into one vector. With regards to the experiments, we used synthetic and real-world data sets. So what we propose is that the interpretability or the explainability of graphs is that if we have, for instance, 5 types of graphs that contain somehow this caveman graph, or other graphs that contain this cycle or the grid or the star or the ladder, belong to 5 different categories. So what we do is that we create a population of 1,000 graphs based on the Erdos-Reyni model with, let's say, random regeneration with edge probability 0, 1. And then for each of these graphs, we inject artificially one of those graphs, so making them belonging to that category. So this means class 0, or instead of injecting one feature graph that is discriminative, we inject an equivalent Erdos-Reyni graph. So these are the special structures that we consider as characteristic and interpretable. And the experimental setup is this one. I think we don't have time to elaborate. And what we do is that based on this, let's say, on the model that we propose, which means finding learning graphs G1, G2, G3, G4. So these are the graphs that we learn, and we visualize them for each of the different 5 classes that we have seen. And so, for instance, for the caveman graph, when we train with the caveman graph training set, we learn this kind of graphs that are quite similar. If you see the caveman graph, these are the learned, the hidden graph 1, 2, 3, 4. These are the graphs we learned that are similar enough to the caveman graph. These are the ones similar, the features learned by the training based on the cycle graph. We see that all these are contained cycles. The ladder graph here, it is not so successful as in the previous ones, but nevertheless, this one should be a ladder graph if there was one edge missing, this one. The star graph also gives graphs that resemble as stars. And the grid graph also finds graphs that are somehow similar. So what we see is that when the training graphs contain structures that we consider discriminant. This is learned sufficiently by the graphs that we learn as features. Here we see a lot of experiments that we conducted. So we have data sets, enzyme, NC1 proteins, NTD that are from the chemoinformatics and biomedical domain, and also IMDb, Reddit, Colab that are coming from social networks and co-authorship networks. These are the features of the graphs, their sizes, the number of edges, the number of categories, the number of graphs that ranges between 600 and 5,000. And for the experimental setup, we adopted a recent paper in ICLR 2020 that was, in our opinion, quite of high impact, because until now there is a relative chaos on how we do experimentation on GNNs. So we applied this methodology of fair comparison for graph classification that was proposed by University of Pisa. And we compared our method to both graph neural networks, to practically most of the existing approaches, but also to graph kernels, which is traditional way to compute similarities that we will see it is surprisingly well performing. So these are the results. So here we have the kernels. Here we have the graph neural networks, and these are the 1, 2, and 3 step random walk graph neural networks. By bold, we have the absolutely best value for each data set, and by underline, we have the best value for deep learning. It is impressive to see that for DD, NC1, and proteins, the best performances are achieved by kernels. And our approach is best deep learning approach in 3 out of 5 cases. And in one case, moreover, it is the absolutely best. And here we have as well on the IMDb and social network datasets, where again we see superiority of the kernels. In 3 out of 5 datasets, they have the absolutely best performance. But with regards to deep learning here, our approach is best in 2 cases. So in 5 of the 10 cases, our approach is better than all the deep learning approaches. And this makes it promising. Then, as a last, I don't know if I have 1 or 2 minutes more, or should I conclude?
Maybe 1 minute. Okay, very quickly. It is not the only effort for explainability of graph neural networks. We have the GNN explainer by Leskovec in NeurIPS 19. So the basic idea is that what they do there is that this approach identifies compact subgraph structures and subsets of the node features that have a crucial role in the GNN's prediction for a training set. And its optimization is based on mutual information between GNN prediction and distribution of subgraph features. They advertise that they have interpretable and good results. And the last approach as a related work is the one XGNN that provides high-level insights and generic understanding. It is based on graph generation. So the idea is that they have a graph generator that is trained to produce graphs that maximize a certain prediction of the model. And in this case, the graphs that are being generated are characteristic of the class that we want to predict. They report good results on synthetic and real-world datasets, and they claim explainability. So this comes to the end of my talk. Thank you very much for your
attention. I am open to questions if I can answer.
Yes, thank you very much for the very interesting talk, which is a very important aspect to explain GNNs. So we have already 2 questions in the chat, so I'm going to read them aloud. How are the hidden graphs created? Are they a design choice, or is something else that you do for them?
Yes, I mean, this is the core of our. So the idea is that let me go back to the motivating slide here. So the idea is that as we have in images, for instance, we are trying to learn matrices that represent visual features, if you recall, circles or edges. Here we are trying to learn graphs that are characteristic, frequent, discriminative in our data, subgraphs, okay? So what we do is that we take a decision. We say, for instance, we will learn 5 graphs of this size, okay? This is a limitation for the moment because we needed to start somewhere. So the number of hidden graphs that we learn is fixed and their size is as well somehow fixed, okay? And via the training process, the adjacency matrix, which means the edges of the hidden graphs, are learned such that the model gives best performance with classification tasks. I don't know if this is answering sufficiently the question.
Yes, it seems so from person asked that, so Luca. And there is another question, is more in general to GNNs, but I'll link it to your method. How scalable is this approach to industrial scale graphs, like millions of nodes, etc.? Or if you can comment in general.
Yes, I mean, if we are talking about millions of graphs, we didn't do experiments on millions of graphs. What we do is that we came up with feasible complexity, which is, where's the complexity? I'm sorry for the continuous scroll. The complexity is somewhere here. It is a complexity, where is it? Here. So the complexity is proportional to the size of the graph, of the input graph, times the size of the hidden graph, which is usually 5, 6, 10 nodes. So essentially it is, because NB is much smaller, it is proportional to N plus M, where N plus M is the size of the input graph. So it seems like a very reasonable time, and this we achieve by doing this transformation that lowers the complexity of the computation. And I don't recall running times now, but the experiments are based on this here, that we have up to 5,000 graphs, and they were completing in within minutes. So overall, it is a method that is scalable based on this complexity, and also learns features that are interpretable, because we can visualize and see what are the dominant features. Of course, I recognize that there are limitations. For instance, that the number of feature graphs and their sizes need to be parameterized from the beginning.
Okay, thanks. And this links maybe to the last question, that have you tried to see these graphs in the real world data sets, and can they help to interpret something?
Yes, this is one of the comments that we had when we submitted this paper. This is ongoing work. It's a very important question. I don't know who sent this question, but it's a very valid question. It is especially in chemoinformatics or in biological datasets. It is very important to extract these feature graphs and have experts sit down and understand and explain those graphs, because they contain domain-based information, which means specific molecules or specific proteins and how they are connected. So this is ongoing work, and I think that's a very valid question.
Okay, thanks a lot. That question was by Stefan, by the way. And
Thank you,
yeah,
Stefan.
for the interest of time, I'd say we can stop here for the
Yes.
live Q&As. And for all of you, you can join the WonderMe channel of this workshop. I posted the link, and you need also a password for that. I also posted that in the chat. And thanks again, Michalis, for the nice talk. And
thank you for inviting me.
Yes, and we'll catch back after 20 minutes or so. Yeah.
Thank you.
Okay, so hi everyone. I hope you enjoyed the break. We are now going to continue the workshop with the next section, where we will present 2 accepted papers from the workshop. The first one is Corgi, Content-Rich Graph Neural Networks with Attention by Joyeon Kim, Tajis Alaminis, and co-authors. Unfortunately, the authors were not able to be here for the presentation, but they have sent a recording. So I will show the recording, and hopefully one of them will be able to answer your questions. So here's the video.
I am Miltus from Microsoft Research.
Can you see it and can you hear it?
Today I would like to present Corgi, a graph neural network that takes into...
Okay.
Hi, I am Miltus from Microsoft Research in Cambridge, UK. Today I would like to present Corgi, a graph neural network that takes into account the rich content that can be found within nodes. We often represent the data in some domain as a graph, and this graph representation usually takes some entities of the domain and their relationships to form nodes and edges among those nodes. However, this graph representation of our domain is usually a projection of the real thing, and as a projection, it's quite lossy. In particular, there are many domains where there is rich information that is lost. For example, some nodes, some entities might be associated with rich content, like huge amounts of text or images, and so on. What we want to do in this work is to take advantage both of the structure of those graphs, but also add additional content information within nodes. Here are 2 recommendation settings where they are often represented as a graph, and the recommendation is performed over that graph, but this representation of the graph is quite lossy. First, it's Goodreads. Goodreads is a website where users can rate books. And with that, we can create a bipartite graph of users and books, and an edge between a user and a book has a value which is about the rating that the user has assigned to the book. Now, through the structure of this graph, we can learn useful information that a user likes or dislikes a particular set of books, and we can recommend other books to the same user, and so on. However, we miss the important content information of books. Books can be associated with, let's say, a summary of the book or a title. And this information is actually quite critical when we do book recommendations. So what we want to do with Corgi is to use this content information of books during our recommendation process. But we also want to use the structure of the graph. So we want to combine these two. Another example is ED. This is an education setting where students answer questions in, let's say, simple math questions. So again, we can create a bipartite graph of students and questions, and an edge between a student and a question is whether a student answered the question correctly or incorrectly. So this is good. Again, we can maybe figure clusters of things that are very easy or very hard for a student, but in order to do that, we're also missing important information. So in this case, the text or the description of the question. In this case, for example, you can see something about a polygon and an angle. That's going to be actually quite useful when we are going to make a recommendation about whether a student is going to be able to predict to answer correctly or incorrectly an answer. So, of course, in existing work, a lot of graph neural network-based work and recommendations do use information about content within the node. However, they do this in a relatively simple way, and as we'll see in the evaluation, this is not going to work quite well. So some nodes are associated with content, and the idea is that we create some form of a function, an embedding function, that takes this content, which could be a long string of text, and we squash it down into a small vector. This vector that you can see here. Now, essentially, within each node, we took maybe a full summary of a book or a full text of a question in math, and we represent as a small vector, usually something that has a dimensionality of 64 or 256 or 512. And then this is the representation we use to initialize our graph neural network. And then we go and do graph neural network-y stuff. This is quite lossy because, well, this rich information, like a full paragraph of text, cannot be easily compressed into this small vector. So we want to do better, and we want to incorporate the content information directly into the GNN, not just as a pre-processing step. So I hope that I now persuaded you that using the content information is both important and that, at least conceptually, existing methods don't work as well. They are very lossy. They lose a lot of information when they consider the content. So what else can we do? To answer this question, first let's have a look at how message passing graph neural networks work. Each node does exactly the same computation. So let's focus on one. Let's say this node is called F. Now, node F does the following. First, it gets its neighbors, in this case D and E. Then, using the state of the vector of D and E, the type of the edge that connects D to F and E to F, it computes a message. A message is just a conceptual notion, and it usually implies a vector. A vector with information that is pertinent to D and F through that specific edge. Now, once we have this message, we want to summarize this information in a permutation invariant way. Neighbors don't have a specific ordering. And once we do that, we take this update X here and we update our current state. So as you can see, essentially, this happens across all nodes simultaneously. So this is the inner loop here. And we have multiple layers for doing this. So in this case, T+1 layers here. So this is great. This is the general framework, and we're not going to change that. Instead, what we're going to do is we're going to change how messages are computed. By changing how messages are computed in Corgi, we are going to allow nodes to take into account the rich content information in a way that helps not just compute messages that take into account the content, but in a way that these messages are personalized to each node, and specifically in this diagram to node F. The next problem is, how do we encode node content? And I mean encode it beyond a single vector. Now, there are many ways of doing this, and let's say this content, this document-like thing, is associated with this blue node here. Now, if we have text, we have many models from natural language processing that allow us to create content encodings for each word or each subtoken within this text. So classic examples include Word2Vec, and more recently, of course, transformer-based models like BERT and Roberta. And of course, bidirectional LSTMs, which have been used in the past. All these methods, what they do is they take this sequence of words or subtokens and map them again to a set of vectors. These vectors have contextualized the information, but still have a lot of information about each part of the text. So we don't have just one vector, but we have as many vectors as words, for example, that we may have in our document. Of course, the content doesn't have to be necessarily text. We can also have images. So in that case, a convolutional neural network might help. Or we might have arbitrary sets of things. So a set transformer could be actually useful here. So let's make this slightly more specific. So in most graph neural networks, in order to compute a message, what you do is you get the representation of node 1 and the representation node 2, so two neighbors, and you use some layer. This could be a simple linear layer or an arbitrarily complex neural network that then computes a message that should go to node 2. And while this is useful, it again misses information about the content of that appears in node 2. Instead, in Corgi, what we're going to do is the following. We're going to use exactly the same structure as you see here, but we're also going to take into account information about node 2 and specifically its content. As you remember, we have encoded the content of node 2 into a set of vectors that have been contextualized, and we want to use information from the previous state of node 1 and node 2 in order to compute a message to node number 2. This is very different from having just some initialization of each node to information about its content. At each time a message is computed, the full states of the encoded content are used and can be accessed by the model. So let's go and look at this and more specifically. The attention mechanism has the following form. It takes into account the hidden state of node 1 and 2 in the previous time step. Then it uses some attention mechanism over the encoded content of node number 2 in order to compute a message for node 2. In our book recommendation setting, we have two nodes that are neighbors. We have a book node and a user node. And what we want to do is we want to compute a message from the book node to the user node. In order to do that, we want to consult the rich content of the book. So this could be a summary that looks like this. And in order to do that, we use an attention mechanism. The attention mechanism takes the previous state of the user and pays attention to the encoded content. When we have the attention-based information, which is what are the aspects of the summary that are relevant to the user, what are the things that she likes or dislikes, and then we concatenate them and pass them through a linear layer. This gives us a message directly to node 2. In practice, this can be quite costly. So we use a caching trick, which is described in our paper. The idea is that we cache these hidden states and we compute the attention only once, saving a lot of computational time. So far, I've described at a high level how Corgi works. Now, the question, of course, is, does it actually work? And here we're going to do an evaluation over the two datasets I previously discussed, so the GoodReads and the ED dataset. As you could expect from this workshop and what I've told so far, the setting we're interested in is recommendation. So we have a bunch of users and a bunch of books, for example, and some users have rated some books, but not others. What we essentially want to achieve is we want to predict the value of edges that have not been observed. So how much will this user like this book? A lot or not at all? So the first thing I need to do is to persuade you that models that do not take into account the content are worse to models that do take account the content. So here what you can see in this table, which is admittedly rather large, is for GoodReads the root mean square error. So lower values are better. Whereas for the ED dataset, which is a classification setting, the accuracy, which of course higher is better, the area under the ROC curve or the precision recall curve, again, the higher is better. What you can see is on the top, we have two methods that are not graph neural network based. And as you can see, these perform worse compared to Corgi. The same thing happens also for graph neural network based models that have no notion of content. So here we do not provide any information about the summary of a book or the text of a specific question. And as you can see, this is among a few runs, what you can see is that our models are statistically significantly better both in RMSE and accuracy for both these two datasets. Now, of course, using content is important, and there are good ways, as I discussed early on, about using the content in graph neural networks. Specifically, as I mentioned early on, we can initialize node embeddings with information about the content, and then just use a plain graph neural network. So in this case, you see GCN, GUT, GRAPE, GENE, and JK LSTM as 4 quite good models, quite well-known models, where the main difference here compared to the previous slide is that we initialize them with many different ways. We can initialize them by using a bag of words or a neural bag of words, or taking a BERT style model and use the CLS, the first token of BERT, or average pooling the embeddings of BERT, or using a sentence BERT, SBERT. And you can see this for different kinds of neural networks, of graph neural networks. And as you can see, again, although the performance improves compared to the previous slide, these are still worse compared to Corgi. And the reason here is that this squashing all the content into initial node embedding in some way or another, what happens is that this simply doesn't allow as much information to flow into the model, and not as much information can be used during recommendation. And this is true both for Goodreads and the ED dataset. So in the previous slides, I hope that I have persuaded you that employing the content is useful. Employing the content not just as a node initialization, but integrating into message passing is even more useful. But there is one specific place where things are much more interesting. The graph structure gives us a lot of information, and we can get away without using the content in more dense regions of the graph. So books and users that have been rated and have been rated a lot and have been rating a lot of books. However, in sparser regions of the graph, so in places where the degree of the nodes is less or equal than 10, what you can see is that Corgi excels. And this is because the content provides useful information that is not within the graph structure and can help get better recommendations compared to models that just use an initialization of the node embeddings. And again, this is because we have rich access to all the information within about a book summary or the context of a specific question. Before concluding, let me just say that in Microsoft, we find graph neural networks very useful for recommendation setting. The Microsoft 365 team is actively using graph neural networks in a multitude of recommendation scenarios, and they are hiring a principal applied scientist in London. Feel free to apply at the link below. In Microsoft Research on the right, we're also hiring interns and postdocs in this area. Please do contact me if you're interested. To conclude, I hope that I've persuaded you that when we look at graphs and use graph neural networks, we simply look at a projection of the actual problem that we have. Finding ways to better project each domain into some representation in machine learning is quite useful. In Corgi, what we do is we take the rich content and embed it directly into the message passing of graph neural networks and get reasonably good results. So with that, I'd like to thank you for your attention, and I would like to say that I'm really sorry that for personal reasons I was not able to present live today. Please feel free to email me with any questions that you may have. Thank you.
So I would like to thank the authors for sending the video even when they are not able to attend. And I would like to ask if any of the authors are available now for questions. When we discussed with them, there was a possibility of one of them being here, but I'm not sure if he was able to come.
I had a look in the chat, but I don't think I saw him in the participants, so I'm not sure they were able to join.
Yeah, I did the same. So thank you, Gregory, for the questions. I would suggest you to email the authors about it. On the main paper, they did not publish the code, but maybe if you can send them a message, they could share with you. So now we can go for the last paper of this section about referral prediction in healthcare using graph neural networks by Regina Duarte and Claudia Suarez. So please feel free to start your presentation.
Thank you very much, Ted. Okay, my name is Regina. I'm presenting referral prediction in healthcare systems using graph neural networks. And this work was done with guidance and support with my professors, Shui Han and Claudia Suarez. So let's discuss the main mechanism that I will talk about, that is the medical referral mechanism. So here we are talking about a patient that is sick or has something and wants to see a doctor. And normally he goes to see a primary care doctor. And then the thing is, primary care doctor diagnoses the problem, sees what he can do. And if the problem is some specific related, the primary care doctor refers to a specialist doctor. And then only after that, the patient goes to see a specialist doctor. Okay, so the thing is, the referral mechanism is where the primary care doctor refers to a specialist doctor, and it's not up to the patient, right? So what we are interested about are in the effects of these mechanisms, how these mechanisms affect the patient care, or how these mechanisms affect the patient satisfaction, or even the healthcare costs. And another question that we may ask is how these mechanisms, these referrals are done. So the primary care doctors refer to specialist doctors within the same healthcare center, or they refer to some colleagues of the med school, or anything else, we don't know, or we have an idea, we can idealize, but we don't know. And this is the main questions that we want to answer. So in this presentation, I will focus on one particular question, which is, if we had a social network of the doctors, if this social network could help to predict the referrals done by the doctors. And this will be our research question for the moment. So to do this, we have data. We get data from a Portuguese healthcare provider, a private healthcare provider, and they sent us two data sets, one from consultation transaction, that had appointments from 2012 to 2017, and have 12 million records. This was from 7 different hospitals, and the records have like date and location of the appointments, as well as demographic of the patients, like their gender, their age, and also the doctor identifier. And then we also have a data set of doctors, like the information about their demographics and also their education. So where they studied in, where they did their internship, and where they work on now, and obviously their specialty. So as you can see, we have 389 primary care doctors and 1,313 specialist doctors. Okay. So before we begin into the main question, I want to talk about some interesting patterns that we found in the data. The first one is the density of male and female doctors that we saw in the data set. So here is like 3 subplots of the 3 major medical schools of Portugal. And you can see that in about 1980s, there is an increase of female doctors. And this is the cause of this is that the Portugal has a dictatorship that ended in 1974, and this kind of similar pattern in the both subplots can be related with that. The second pattern that I want to share with you is the number of doctors who the patients had appointments with follows a parallel distribution. So normally the majority of the patients had appointments with only 1 or 2 doctors, and there is a few patients that have appointments with lots of different doctors. Okay, and the third and last interesting graph is that normally the specialties, the doctor specialties, normally the number of consultations stayed constant through time, and the only one that increased was general and family medicine specialty, which really is the specialty of primary care doctors, which is kind of interesting, right? So okay, let's go ahead for the other question. Okay, we want to answer if a social network of the doctors could predict the referrals, right? So the first thing, we have to discover the referrals and then produce some kind of way to deal with it. So here we take some assumptions to kind of have a proxy to do referrals to the original referrals, and for this we assume several things. So let's say we had a patient that he has his first appointment with a primary care doctor, okay? And then let's assume that the same patient gets a second appointment with another specialty doctor. And we assume that if this the time elapsed between these two appointments were less than a month, we assume that the primary care doctor referred to the specialist doctor. Okay, so this kind of interactions between primary care doctor and specialty care doctors were like, we say it was an interaction, and here it's the plot of the cumulative distribution of interactions, and you can see that the ones that are within 1 month are about 23%. So yeah, the referrals are 23% of the whole interaction. With this assumption, we just build a graph, a referral graph, which had the referrals as links and the doctors as the nodes. And as you can now foresee, this is a weighted bipartite graph because, well, it's weighted because we count the number of interactions or referrals that each primary care doctor did to a specialist doctor, and is bipartite because we only have referrals from primary care doctors to specialist care doctors. And then in this graph, we had only 284 primary care doctors and 839 specialist doctors. So following some analysis of this graph, before we go along, as you can see, the many physicians that are in the data sets, in the original data sets, don't link in this referral graph, which can evidence some inefficiency in the referrals, right? And the second thing that I want to mention is that nodes degrees in this referral graph follows a parallel distribution, meaning that there are just one or two or a few specialist doctors that are like hubs and receives a lot of referrals, and there are many specialist doctors that just receives one or two referrals. Which implies also this kind of inefficiency. Okay, next thing is like the social graph, you know. So we have referral graph, okay, but we also have to have a social graph to get an information about this and to kind of answer our question. Okay, for this we have also some assumptions, and here we just assume several things about who knows each other in the doctor's scenario. So here we assume that the doctors who work in the same hospital know each other, and so they share a link. Then we also assume that doctors who did their internship in the same location and at the same time, they also work together. And doctors that did the faculty together within 2 years, we also assume that they knew each other. Obviously, this is a proxy. It's not really the real social graph, but it's the farthest that we got to go. Okay, and for this social graph, we we put the same nodes as in the referral graph, and as you can see, there is a lot more edges in the social graph. Okay, so the thing is, okay, we have the referral graph, the social graph, and we only have a question, that is, if the social graph can really predict referrals, right? Okay, or can help to predict. So what did we do? We grabbed the social graph and computed centrality measures for each doctor, meaning each node. So we computed degree centrality, between a centrality, and eigenvector centrality. And then we grabbed in the referral graph, and this is the part where it gets interesting. We added some attributes to the nodes, some simple like gender and age, and also the social network attributes from the social graph. So we added the degree centrality, betweenness, and eigenvector. Okay, and this was done to perform a link prediction task on the referral network, to have a comparison to get a link prediction without the social network attributes and with the social network attributes. So to say if this link prediction if the link prediction task in the model with the social networks outperform the link prediction task for the model without the social network measures. So this was an evidence that really the social graph contributes to referral, and then the referrals made by the doctors are biased towards their social networks. So, and we did this link prediction task with some state-of-the-art algorithms like RecSys and RecSys, and we also did it with Node2Vec as a baseline. Okay, so the results are really something that we were expecting. That was in all the models and in all the algorithms, the indicators really improved when the social information of doctors were present. So you can see, like in RecSys and also in RecSys, the accuracy in the test sets improved from the model without information to the model with information, with social information. There are 3 more attributes, and the loss in test set also similarly decreased. Okay, so this is really an evidence that referrals are biased towards the social networks of the doctors, and this was really the answer that we were searching. But we got a bit further, and we want to see the embeddings produced from these link predictions. So here you can see the node embeddings from the H2VEC model. Here we have, and this is without social features. So these subplots that you can see, sorry, they are very similar. They are the same embeddings. The difference is they are called differently. So the first one is called by doctor type, which is especially a care doctor, specialty, or a current care doctor. Second is called by gender. The third one is called by birth year or age of doctors, and the third one is called by hospital center where they working. So as you can see, the embeddings from the model without social features are not so structured, right? Are not so interesting, and well, we can see really a difference here in gender, but really we don't have some clue about what is happening in the link prediction and what is kind of, it's random, right? So yeah, these embeddings were run from H2VEC, and these visualizations were done with Disney visualization. Okay, but when we compare these embeddings with these embeddings from the model with social features, you can see that it's a lot of difference. So the first thing that we can think about is that in these embeddings, there is a lot more structure in this model. So as you can see, there is the link prediction really have some outperformance the link prediction from the model without social networks, because the embeddings are more structured, you can see some differentiation, and you can see we can make some sense about it. So you can see that some doctors who work in the same hospital are closer together, and it's not so 100% clear, but it's really something that's better than model without social features. So, and this analysis was used also with isometric visualization, and they produced the same results. So the bearings from the model without social feature were also really unstructured, and the model with social features was more structured. And this also more evidences our hypothesis of the importance of social features for the referrals. So this was really our main conclusions. But what we think about is that, okay, the referrals are biased towards social networks, and for the future work, what we can and we want to do is to see if we can build a recommendation system that can be not biased, which will be kind of difficult because data is biased. But yeah, that is our main thoughts. So thank you. And sorry about the network problems about in the early. I have time for questions. So thank you.
Yeah, thank you for the great presentation and very interesting, Regina. We have a question on the chat that Claudia has been answering about possible bias that could be identified by the data set, such as monetary or popularity. Could you elaborate a little bit on that? I see that Claudia has answered, but maybe just by voice.
Yes. So yes, of course, that is. Sorry, someone could. Professor Holly, you can. No. Okay. So let me answer. So yes, of course. Well, normally all the data are biased, and of course this show that these data were biased towards the social network, and our point was really that one. So this was like a normal private healthcare provider. So we assume that it was these patterns are generalized or can be generalized to with some private healthcare providers. And the thing is, yeah, we do assume and realize that these are biased data, but this is kind of our main results, right? They are biased towards the social networks, and the challenge is to accept it and try to find ways to have like recommendation systems to try to deal with this kind of bias and try to get some healthcare referrals that are not biased and can be more efficient.
Okay, thank you for your answer. Do we have any more questions on the audience? Maybe we can take one more. So maybe I can ask one final question. So on the embeddings, it seems very separate, the embeddings from female doctors and male doctors compared to the other metrics. Do you think there's a quick explanation for that, or is mainly because of the way the data was collected?
Yeah, so we when we see these results, we the three of us were really surprised by this kind of 100% separation. We do well, we do assume that there is really some bias towards males, referral to males, and female to female, but we not really feel that is like so separate, and it could be because gender was a really great attributes in this model, and probably if we increase features, it will be more not so separate. This was our guessing.
Okay, see, thank you very much for.
Can I add something about this gender issue, because it's such an interesting thing? Just to say that it is a well-known bias in healthcare referral, that females will refer to other females and males refer to males. So this is actually a very, let's say, interesting social aspect in medical referral, and is also a place where recommendation systems could, I don't know, try to have an impact, like a positive impact in a more, let's say, diverse recommending pattern.
Yes, for sure. Thanks for the answer, and I agree. It could be one way that we could try to mitigate these types of problems. So thank you very much for the presentation, and now we can do a very quick break, and we'll be back at 6 and 10 for the last keynote speaker.
Okay, so hello again. So we'll now have our final keynote talk of the day done by Andrew Jai from Pinterest. So Andrew, are you around?
Yeah, give me 1 second to set things up.
Yep. So I let you prepare, share your screen while I give a few words of introduction.
Sounds good.
So Andrew is currently tech lead at Pinterest, and before that he received degrees from Berkeley and Stanford, and spent as well some time at Google. And at Pinterest, Andrew works mostly on recommender systems, visual search, and computer vision. So today, Andrew will be telling us in more detail how graph neural networks are used for recommendation at Pinterest. So, okay, Andrew, whenever you're ready, the virtual floor is all yours.
Yeah, sounds good. Let me know if the audio has any problems or if you can't see my screen.
So right now we see just the P, I imagine, for Pinterest, but okay, yeah.
Yeah, exactly.
Okay, now it's all working. Okay.
Great. So yeah, thank you very much for the introduction. I have the pleasure today of describing some of the work that we've been doing using graph neural networks to help power Pinterest recommendations. I'll try to time things so that there's roughly 35 minutes of content so that we have 5 minutes left for questions. But there's a lot of content, so let's get started. Yeah, so a bit more about myself. I'm one of the senior machine learning architects at Pinterest, leading several teams working on recommendation systems, ML infrastructure, neural modeling of users and content, and computer vision. Pretty much anything deep learning related at Pinterest, I'm there in some shape or form. And today I'm excited to be able to describe sort of how we use graph neural networks at Pinterest. And sort of before I get to that part of the presentation, I do want to give some context on the problem statement for Pinterest. Like, what are our recommendation systems sort of structured? How are they structured? Like, why do we take the solutions that we do? And then dig into how we represent content using graph neural networks, and use that representation to also learn good embeddings for search queries and users. So to get started, Pinterest is the home of inspiration. People come to Pinterest to find ideas, such as what recipes I should cook this morning, or looking for like home aesthetic designs for your next remodel. I've actually been using Pinterest a lot for these use cases. All the recipes I know in this world are stored into a Pinterest board that I've gathered over the last few years. And every time I cook, I bring it up just to remember like what the recipe and the steps are to cook something. I've also been doing renovation recently, and being able to find the style and having a visual reference to show contractors has also been really, really useful. We have over 300 billion ideas organized into around like 6 billion boards. And we surface these ideas through our personalized recommendation and search systems that generate these endless feeds of diverse content like this. Our mission is to bring everyone the inspiration to create a life they love. And we have to do this at scale. So we have over 450 million users across many countries, and we have a huge content corpus. This is what recommendations look like on Pinterest. Here I'm showing you home feed. This is the first thing that you'll see on Pinterest that powers majority of our engagement. We have a lot of diverse content. We have ads. We have these native creator videos. You can see here users have reacted to these videos as well. We have organic content that are linked to a website. This is what I use to save recipes online, as well as products that you can purchase. We want to translate this product into like a technical design. And this is how we structure these systems at Pinterest. The key here is that we need to build a system that can handle tens to hundreds of thousands of requests per second and be able to sort of shift through billions of pins to find maybe the 10 or so that you're most interested in at that moment in time. It all starts with the front end where a user starts the recommendation request. Here, the query is a user for home feed asking for content. So we first need to fetch everything we know about both users and content. You can think of this as all the categorical, continuous, like other types of maybe embeddings that we've already pre-computed offline. We then go to candidate generation. This is where we need to filter through billions of content really fast, like less than 100 milliseconds. Many methods exist to do this. We actually use sort of an ensemble of many, but the most interesting one in this group for this audience may be this graph-based random walk service. Oh, oops, sorry. That was a sneak preview of later slides. But specifically for the random walk candidate generator, what's really interesting about this one is that at one time, this powered over 70% of recommendations on Pinterest. Even today, it's a good majority of the recommendations. So this is very, very important. And how it works is that we've taken the pin board graph. So users can put our content pins into collections we call boards. We have billions of pins, we have billions of boards. And using this graph, we sort of store it in our own internal graph traversal service so that the overall flow for candidate generation is given a user. We get somehow translate a user to pins. One approach, for example, is just take a user's most recent pin activities as the seeds. So once we have those pins, then we can use this pin board graph random walk algorithm to generate hundreds of pins sorted by visit count based on like approximate personalized page rank. And we perhaps like take like 10,000 to 100K steps per request. And a lot of the key here is being able to do all this really fast, like less than 100 milliseconds. But this simple algorithm really works. It is powering the majority of recommendations. It's still, at one point again, powered over 70% of recommendations at Pinterest. The key insight here, though, is that specifically the pin board graph has been very important for Pinterest, and we'll use this also later on in our GNNs. So just to finish this picture, we have candidate generation, shift through billions of content into thousands, and then we have ranking that goes from thousands to tens of pins. Ranking spends more time per content than candidate generation because we really want to refine the results based on our best understanding of users and content. So you can see there's an arrow here as well where we take as much signals as we have about users and content to try to make the best decision. And of course, again, this is all happening concurrently with tens to hundreds of thousands of requests per second. So home feed is just one of our recommendation systems at Pinterest. We also have other important ones like image search and also related pins. But for home feed, we really care about this responsiveness to user feedback. Like user tastes are very dynamic, and we need a system that is able to sort of handle both short-term as well as long-term preferences. But more in general, for all these different recommendation ML systems, we need to be performant in the prediction. That's really the key of success. Can we actually predict what a user is interested in well? Of course, based on the diagram before for scalability, when you handle, we're handling loads for over 450 million users, you can't really do much on the request time, right? We have to handle that entire flow in like 200 milliseconds. If you run just like a standard NLP model, that might already take half the time. So pretty much we don't run these expensive models, GNNs, or even NLPs on the fly. Instead, we pushed these computation offlines that we can use maybe through like embeddings that we can use during the request path. To give you more of a sense of the scale, ranking, for example, needs to score over 10 million items per second with the P99 latency of 20 milliseconds. It has to be really fast. So the key to recommendation systems, of course, is to be performant, to be able to do these predictions well, and that's what we'll focus on today. What are the components that we build using GNNs to produce embeddings of content, search queries, and users that enable us to be as performant as we can in prediction. So it all starts with the content. And for Pinterest, our content are our pins. So we see a pin has many different components, the most important of which is the image/video. But we also do have title. We also have the user that created the content, as well as this sort of indirect concept of that graph. I again mentioned pinboard graph here. It powers 70% of engagement at some time on Pinterest. And really the power of this graph is that it's human curated. People have put the same content into different boards. Here, for example, we have a kite boarding board, as well as a snowboard board. So the same content put into both of these boards has a higher chance of meeting, for example, outdoor sports. So this example might be a little bit simple, but think of it as scale. We have billions of pins, we have billions of boards, and we have tens of billions of edges that connects all these things together. Our hypothesis is that the graph is quite important as well to understand the content. So we need graph, we need text, we need visual, we need all these node features. And you can see pretty naturally that a graph neural network fits this paradigm pretty well. Given the pinboard graph, we can evolve over it with nodes represented by these multimodal features. At Pinterest, our graph is really big. We have billions of nodes, tens of billions of edges, and sort of that limits what we can do at scale. But over the years, our GNN approach has still evolved. We started with two-hop neighborhood sampling with a more traditional graph stage architecture. And since then, we've improved both how we learn these embeddings, like the loss functions we use to learn these embeddings, as well as our choices in how we do random walks. So for example, here, like instead of doing two-hop neighborhood sampling in the beginning, now we're doing a random walk-based neighborhood subsampling, which we know is quite performant because this is the exact same technique that we use to power 70% of engagement on Pinterest. For in our case, we use around 50 neighbors per node. And this is all happening on the fly during training. One other detail here is that we actually need our GNNs to be inductive. And this is because new content gets added to Pinterest every second, and we need to generalize to that. Like a naive transductive model would require us to learn the IDs of every new node. Well, here we can just run our pre-trained GNN architecture. A new node arrives, we fetch its node features, and we can run the pre-existing model on that new node to get an embedding. Over time, the graph becomes stronger, and that content just does naturally better as the graph changes. So now I'll describe like the most recent evolution of our architecture. You won't find this in the paper that I linked before. We're given the self node. We have around 50 random walk neighbors. And we have the multimodal node features for each one of these 51 nodes, one for self, 50 for neighbors. These are flattened and then passed through a transformer encoder to combine into the final embedding. The summarized output is passed through MLPs and also gets L2 normalized to produce that embedding. These decisions of separating the features for visual, for text into separate inputs are just empirical based on internal data sets. So now that we know how to encode the information, we have to also see how, like, what is this learning objective? So yeah, overall, again, we have billions of pins and we want to learn the semantic meaning for all these content. So we structure this problem as a metric learning task where we use the recommendation system feedback. For here, this is an example of related pins where, given a query pin, users have interacted with our feed of results and told us, like, what is, for example, something that a user would repin or something a user would click. These are weak positives. We have negatives as well. I'll go into them more in the next slide. It's a bit complicated because negatives are really where we care about, for example, how to de-bias ourselves against popular content. I'll explain that a bit later, but for now, the overall idea is to push similar pins closer together based on weak positive signals and push pins that we don't think are as relevant further away. Over the years, we've also changed this loss function. Like, there's a lot of ways to do metric learning. We stuck to many years actually just using triplet loss. Using triplet loss with distance weighted sampling for negatives. Now, though, the most recent variation that we have is sampled softmax for retrieval. And sampled here comes from the fact that we're not computing the softmax denominator over 1 billion pins, right? Instead, we're just using the denominator are just going to be the positive and negative pins in our batch. So I said I'd talk more about negatives. This is what we'll do here. We actually use two types of negatives to learn our model. One are random negatives from our corpus. So we have, for example, 1 billion nodes that defines our corpus, and we randomly select a portion of our batch to just be those examples. The idea here is that when you try to find maybe like thousands of examples within 1 billion batch, the likelihood of what you sample being relevant to the query is quite low, and we just use that information to learn our embeddings. But we also use, I guess the most important thing here about random negatives is that these are not necessarily content that our recommender system even shows, right? These are not impressed examples. They can be not impressed examples. We've actually seen that this is quite important to use in learning our GNN. We also have like in-batch negatives as well. These helped actually a bit with relevance, right? So we want to use at least impressed negatives as well. So this is over here. And the intuition here is that impressed negatives are going to encode that popularity, right? It's going to encode the recommendation system bias, like that power law distribution we always hear about. So using these types of negatives, we've seen it actually helps quite a bit in terms of relevance. And they're defined that, so intuitively, these are at least impressed examples. This is some more details about how we build this softmax matrix. So we particularly separate these two types of negatives into their own sampled softmax losses. So we have two losses for two types of negatives. This was just better in our offline measurements. So I mentioned again, this popularity bias effect is sort of quite challenging to circumvent. And this is an additional trick on top to actually help with this problem, where we can apply probability correction to sampled softmax. Think of it as applying a per logit bias that can be applied. Here is the correction. The intuition here is that this bias is not learned. It's computed analytically from, say, like impression counts that the recommender system has had for your data set. There's a mathematical derivation of sort of what this correction means. And I'll leave the details here for a more rigorous treatment. But intuitively, the idea is that when you use popular content, like our positive, the in-batch positives as negatives, you're going to sample popular content, the same popular content over and over again, much more likely, right? This is that power law distribution. You'll probably have like 1 million pins that are sampled majority of the time for in-batch negatives. And naively, what happens then is that we strongly push these popular examples further away, right? We see these negatives so many times in our data sets, we just want to shove them into a corner of the embedding space that we don't want to deal with, but that's actually not exactly what we want in our recommender system. You've seen instead, if you apply this correction, so this probability will be high for popular content because Q represents the class sampling probability, the likelihood that this pin would be in our batch. For popular content, this number is higher. And what this actually does is that with the correction, popular content has like a larger negative bias that allows us to, that in like the derivation of softmax, we see that what happens is that the gradient to popular content is reduced. So even though we see this popular content many times in our batch, we don't shift the gradient that much. And this has actually helped a lot in terms of our offline metrics. The reason why we applied this particular correction to the sample softmax is really because it has a mathematical intuition behind it. It allows us to think of this problem in sort of a more probabilistic formal setting. Combining everything I described, you get PinSage, where compared to visual, you see that visual is just less semantic. Text is semantic, but it's not visually consistent. For like a platform like Pinterest, this actually matters a lot. Pixie is equal to random walks, and it's sort of random. It's also semantic, but also not visually consistent as well. Well, PinSage sort of has the best of all worlds. It's semantic and it's visually consistent. Of course, we also care about these quantitative measurements, where we've seen so here, the high-level summary is that our graph neural networks produce the best content embeddings. But sort of how we determine this is through our internal data set. We measure over many days, right? The graph changes, so we need to understand performance after training our model for many days. And what we see is that compared to just visual embeddings alone or text embeddings alone, or even the combination of text and visual together, PinSage, which is a line that I actually forgot to add, unfortunately. PinSage is better. Like using graph neural networks, combining the pinboard graph along with all the multimodal features produces the best, significantly the best content embedding. And we've had a lot of success with this, like over 70 launches, lower bound. This is a lower bound mostly because the way we track this is through spreadsheets more than anything else. Which makes sense, right? Because anything that needs to understand content at Pinterest, whether it's the recommendation systems or even trust and safety to classify content into safe or not categories, will need a strong content representation. I spent a lot of time going into the details of PinSage because it's quite important, and I'll show you why. Like PinSage is actually the foundation. This GNN is the foundation of how we learn everything else. Search queries and users are specifically what I'll go into today. Let's start with search queries though. The problem statement here is like given a search query, like where a search query is represented by text input, how do we produce an embedding? What does that actually mean? Like how do we want to learn this representation so a search query embedding is meaningful? The general idea is that we have image search on Pinterest where a user types in queries like chicken recipes and gets a feed of results. Very similar to what I described before, we have a lot of weak supervision from this. Some examples are a user is looking at kitchen taps and sinks and purchases this specific faucet, or a user repins this dog, animal, lion drawing when typing in this query. Some users might just click on the result as well. For example, here, they click on this creamy garlic shrimp recipe when there's like a Whole30 shrimp recipes query. Different action types are actually more informative than others. For example, we found that purchases are really effective as a supervision signal because it's very clean. If you're involving money in anything, this is a very sparse action, but when you have it, it sort of is more, a single purchase is pretty much worth more than say multiple repins and many multiple clicks. So that's like the overall a formulation of what we want to do. Like, let's use our content. Let's use our content to learn that search query embedding, right? Content feedback, use that to learn something meaningful for search queries. And that's what we do. So a lot of components here are the same as before. It's very similar to the pin stage training. On the positive side, we just use the pin stage embeddings, the GNNs, and whether or not you train that GNN end to end, or you just use the pre-trained model, it really is up to you. We've seen mixed results actually with this. Sometimes it's better to train these models end to end. Sometimes it's better to just use the pre-trained model. But here the positives are pins, the negatives are the same as before. We have random negatives, we have in-batch positives as negatives. The query side is different. So here, given kitchen taps and sinks text, we went through many different model architectures. And the one that sort of had the best performance and with trade-off, of course, with serving costs, was this Dilbert model, where you tokenize input text, pass it through these like transformer models, produce that embedding, and this metric learning loss is the same as before. We see on the left here, just more evidence that PinStage produces the best search query embeddings compared to visual or text alone, also compared to both. We evaluated these embeddings over product search as well as organic search datasets. So here what we did was we have user feedback and we can calculate recall at 100 metrics where given the search query, generate a bunch of pin results. We have labels on the pins, like we know which ones a user has repinned or here long clicked. So we can calculate recall metrics for both shopping as well as organic content. And you see using visual in that learning objective I showed before alone gets this baseline performance. Using text gets you a lot better, but using PinStage gets you even better, combining everything together. We've had over 10 launches of this as well, mostly in the search stack across many different verticals: advertisement, shopping, organic, and creators. One highlight here is that we were able to improve the long clicks, which is a proxy for purchases, because again, purchases are very, very sparse actions, as well as impressions on products by 11 to 8% respectively on product search, using search stage directly as retrieval. Here, because we learn things in a metric learning task, we can index our content embeddings on our corpus, use a really fast approximate nearest algorithm like HNSW to be able to use search stage on the query side to find the nearest neighbors for candidate generation. These numbers were, in retrospect, were quite large. So let's pretty much ask the same question for users. How can I learn a user embedding that's actually meaningful? How can I capture this like dynamic nature of users over time at scale? One of our prior works here is that we took the user activity sequence of content and did unsupervised on-the-fly clustering on top of PinStage to generate multiple clusters, which we found to be semantic, right? So here, given some recent user activities, we have PinStage embeddings for all of them. We can generate clusters using an unsupervised approach and find that these clusters have meaning because PinStage is quite strong in terms of semantics. For this particular user, we found technology, we found recipes, we found this globe, interesting taste. So each one of these clusters then can be represented as the user embedding by doing something like take the medioid of that cluster, use the PinStage embedding of the medioid as the user embedding. With this technique, go from one user embedding to multiple pins. If you remember before when I talked about like Pixie random walks, this is also as a candidate generation system for home feed. This is a way to do the user to pins component of that stack. This has also been very effective, 10 plus launches, and you can one of the validations for the success of this approach is that we use this for retrieval. Like I mentioned, one difference for this experiment was that user to pins was through pinner stage, and then from a pin, we used PinStage to PinStage to generate candidates. This led to around 3% increase in engagement volume on home feed, and home feed powers majority of engagement on Pinterest. So this was quite significant as well. Now, of course, like the next thing we want to do is try supervision in deep learning. We had a lot of success with the simple unsupervised clustering approach, but we as a team believe pretty strongly that a supervised deep learning approach should be more flexible and can do better. So the question then is, how do you take this user sequence and learn that user embedding? And here particularly, for this work, we aimed for one user embedding, just to start simple, and also because we've seen from experience that multiple user embeddings has some challenges when you integrate it into systems like ranking. So for this work, what we first had to do was produce the entire pin activity sequence of a user across all of Pinterest for an entire year. Here, maybe a user first was on related pins and clicked a pin. And then maybe 2 months later, they go to home feed and click repin this other pin. And then maybe 8 months later, they go to search and repin this other pin. Some users have fairly long sequences, like tens of thousands, hundreds of thousands of actions. So we have to deal with that. To train our model, what we first do is, given the user sequence, we randomly split the sequence. This is done per user, so every user has a different split during training. And this is also happening on the fly. So if we finish an iteration, go back to the same user, we would select a different random split. Next, we encode the last k actions via a model like a transformer. And here we have k equals to 255 currently, but we do experiment with other lengths as well. The general intuition here is that the longer the length, the better. But for infrastructure restraints, currently we're at 255. This previous, this encoding produces one user embedding. And then we use that one user embedding to predict actions in the future. This part is a little bit complicated, so I'll go into that in a later slide. What exactly do we do? What's the loss function there? So this is the high-level architecture of what we described. We use a transformer, something very common now at Pinterest, to encode the last 255 actions and summarize into one embedding. We use the same metric learning loss again with same types of negatives, but here the positives are represented as like the next actions in that sequence. These are the pin sage embeddings for the next action. You can see the setup here is similar in training to both pin sage and search sage, where it's a metric learning task. We want users to be close to the positive actions in the sequence next, because we believe that what you do when you randomly split a sequence, there should be some meaning to what's happening afterwards. And negatives are the same in batch and random negatives. And the way we do that is just through some complex NumPy indexing to get that working. The intuition for the random negatives, by the way, is the same as before. Like with billions of content, when you randomly select thousands of examples, the chances of those examples being relevant to the given user at that given time is quite low. So that's why it's an effective negative sampling strategy. The loss function itself is quite complicated. There's 3 components to it that I'll describe. But we're actually trying to simplify here. So maybe in the future, this will be different. But let's see if I can explain this well. So one intuition is that we wanted our embedding to understand short-term interests. If a user has a change in taste, we want to make sure we're responsive to it. And this is done through next action prediction. Given the encoding of a user's past actions, we use that embedding to predict the immediate next positive. So this is through metric learning again, where user embedding, the positive is this next pin and the negatives are the random corpus. We found then that instead of just predicting the next action, we can also do a dense next action prediction. And this is because the transformer has an output for every element of that sequence. What I mean by this is, given the input sequences to the transformer, you have an embedding per output. And then we can actually use a causal masking to make sure that a produced embedding can only attend to the previous actions. It turns out when we did this, our architecture basically became like a small GPT architecture. oops, let me go back. Yeah, so doing it this way, where for every single element, every single user embedding produced in the transformer, it only attends to previous actions, and we use that embedding to predict the next element in the sequence. So here, E(t)-1, the metric learning task would do is the positive would be the next action here. This mostly helps because it's much denser supervision that, yeah, mostly because it's a much denser supervision than simply the next action at the very end. The final loss function component we have is trying to consider the long-term user interest. What we found is that if you only consider the short-term interest, our model is simply learning to attend to only the most frequent, like the latest actions in that sequence. But we also want to make sure that we understand the user's overall tastes, not just something very specific to that moment. And we do this through using a window for positives in the metric learning loss, where we have a 14-day window, and we use every positive action a user has had in the next 14 days, where given this user embedding, we have multiple positives and we compute the similarities to all those positives, and the negatives are still random negatives. This allows our model to attend to longer time, to longer events in the sequence. Overall, we found that this loss function is actually the most important one out of the three. So to summarize again, we have the user sequence for a year, randomly split it, and code last k actions, here specifically 255, and we have these three loss functions to predict actions in the future. So we see on the left that we're able to do better than the previous approach on some offline eval, but more importantly though, to sort of show the impact, we evaluated this user embedding in home feed ranking, where we saw very substantial lifts. So here we replaced the unsupervised clustering approach with this new supervised embedding. Not only was it cheaper, but it was also able, because it's one embedding instead of multiple user embeddings, we were able to increase time spent on Pinterest by 1 to 2%, overall engagement by 3 to 4%, and reduce the amount of hides, like the user explicitly hiding content, able to reduce that action by around 2.6%, to show that we're showing results now that users like and engage more with. It also lifted everything we care about across shopping, creators, and organic. And in order to prove to you all that GNNs is what made this work, we ran a feature ablation experiment where we tried two things. We first, given the baseline, which is using all the features we have, we tried removing the most important feature, retraining the model, evaluating it, and the most important feature was pin stage. We then kept the most important feature, but instead we removed the second most important feature to see the effect there, like what happens. So what we actually did was we removed every single feature one at a time, and then we just sorted the results based on which one, based on the gap of performance compared to baseline. And you can see here, pretty much nothing else matters for this user model. Like if you remove pin stage, your performance caters. Craters down to like less than half the performance. But if you remove the second most important feature here, whether it's the time of the action, whether it's the action type, the performance barely drops. And this is my last slide. So to summarize, we've seen that GNNs produce strong content embeddings, which are fundamental to our understanding of queries and users. We also have a lot more entities in Pinterest to understand, like videos, creators, products, that we're exploring GNNs as well with. For example, products is interesting because we have this graph of merchant to products that we want to use as well to essentially have a better prior to understanding what that product can be. Like certain brands are known, like Nike, for example, are known for shoes. And if you're a pin in the Nike brand, if you're connected to that Nike node, they should be able to tell us a bit more about the content. It's also quite challenging to improve the performance at web scale, right? The techniques that we can do with billions of nodes and tens of billions of edges are quite limited because oftentimes you have to also invest in some custom infrastructure to just be able to run one experiment. So like a lot of times you have to take a bet, and right now the bet that we're taking is that if we can go to heterogeneous graphs beyond bipartite, that would be another big win. And intuitively, the pinboard graph is quite important, but we also have a lot more relationships. We have the users that created the board. We have creators that a user follows. The idea of the videos, the native content that that creator produces, as well as sort of this like product merchant relationship. If we can encode our entire ecosystem as a graph and use a GNN over it, it would give us probably the strongest priors we can have to understand that entire ecosystem. We've also seen it takes more than the GNN alone for good performance. What other areas that we explore, of course, are the loss functions, the features and data that we use. And we've seen that larger parameter models actually are quite effective. So we want to reach like the billion parameter scale for some of these models. Mostly the challenge there is figuring out how to serve it in a costly manner. And of course, I need a self-pitch here for hiring. So if you're excited about this work, please join Pinterest and help us build this home of inspiration for everyone. I've left the career page here. And yeah, that's it. This is my last slide. Thank you all for listening.
Thank you, Andrew, for the great talk. So we have time for a few questions. I see that in chat we already have a couple of them. So we will start with the first one. So I think it was related to slide 32. So the question by Luca is, what is a long click? Isn't product impression somehow what you decide as Pinterest? Or you mean you are able to recommend more content?
Yeah, it's a good question. So for products, I think ultimately would care about measuring purchases. So this is for a lot of retailer websites, it's measuring like gross market value. And purchases are nice because if we, given like a search query, if we see a product and we know a user purchased that product from that search query, it's a very strong positive signal. But purchases for Pinterest currently doesn't happen on site. It happens when you click a pin, go to the website underneath, like maybe Nike.com, and then you do your purchase there. So that relationship, tracing it, attributing it back to Pinterest is sort of challenging. So we need a proxy metric. It's also sparse, by the way. So we need a proxy metric that sort of is like really correlated to purchases. And we found that this idea of long clicks, going to that website and staying there for over 10 seconds, or it's either 10 or 30 seconds, I actually forgot, is correlated with purchases.
So you have the time that the user spends on the external site?
Yeah, mostly because they go to the external site and then they come back, and that delta is the time.
Okay, thank you. Second question by Gregory is, are pins and pinboards represented in the same graph?
Yeah, so our graph is bipartite. On one side is pins, the other side are boards. When we do a random walk, we actually try to generate lists of pins as results. So we actually take 2 steps every time, where we go to the board and come back to the pin.
Okay, thank you. A question by Andreas. How do you parallelize pin usage across multiple user embeddings? Do you use the same transformer network?
Yeah, it's a great question. It's the same transformer network for multiple users. And that's actually the beauty of this approach, where we're able to learn parameters of, so for example, like core users, ones that engage with Pinterest the most, they'll help us learn parameters that we can then also apply to these like low signal users, like users that are not as active on Pinterest.
Okay, thank you. A question by Jayun. How did you implement the connection of the graph? If you put it in a matrix, it will need too much memory. So I guess it's about the random walk, right? But yeah,
it's a good question. I think there's a lot of things here. To give you some details, we don't do like a exact random walk. We actually implement an approximate approach to that random walk for it to be more efficient. And a lot of the details about what we do, like essentially our graph store is just very careful C++. But I can tell you that under the hood, we use the snap library from Yuri's group at Stanford.
Okay, thank you. So maybe the last question. which is actually two questions from Sufyan. So concerning the new code, so the cold start pins, how much importance do you give them? Is initializing the embedding with neighboring embeddings enough? Do you have a dedicated evaluation for these cold pins items?
Yeah, so exactly. We have an evaluation specifically for like low degree to 0 degree content. And we actually learn our GNN so that even if it doesn't have the graph at that point in time when it's first created, this is something simple, right? Just through dropout, we're still able to do fairly well. A lot of this is also sort of mitigated through good infrastructure where we have infrastructure that is event-based, where every time a user repins a content or engages with like content, we can recompute that embedding. So the first time a content is added, it has no graph, but maybe like a few seconds later, it will have a graph connection. And then we can update that with the GNN. And over time, it just gets better. I think in general, we see that within the first 7 days of content, the graph embedding is sort of less stable as it's trying to get more connections. But then after 7 days, it's quite stable.
Okay, thank you. And the last question is, for user embeddings, do you take into account non-uniform time difference in consecutive user actions, seconds versus hours versus days?
Yeah, exactly. That's actually a feature in the model, like the time delta of actions. And we use like seconds, hours, days, weeks, years as well. The year one probably doesn't make sense because we only train over 1 year.
Okay, so thanks a lot, Andrew. I think we are done with the questions. So it was a very, very productive session, I think. So I think it is time to wrap up the workshop, except just to be sure there is no more questions to Andrew. Is it okay? Yeah. Okay. So So to wrap up the workshop, I think we had a great panoramic view of how graph neural networks can be used for recommendation. So we had some academic and industrial perspective. We also had some nice talks on how side information such as knowledge graph and text data can be integrated into GNN approaches. Also some insights on GNN explainability. We also learned about some new applications such as referral doctor prediction, which I think can be of interest for the RecSys community and maybe leads to more research in that area. So I think we had today a very complete and enriching program. So as it is Saturday and already an advanced hour for some of us, I won't keep you around much longer. But just I want to mention that if you have any feedback or criticism on the workshop that you would like to share, please don't hesitate to reach out to us and let us know what you enjoyed, what we could have done better, or if there is anything that you would have liked to see. And finally, as closing words and on behalf of all the GReS organizers, I would like to thank again first the keynote speakers who kindly accepted our invitation and gave very insightful and great talks. I would also like to thank the paper presenters and authors. Thanks a lot, everyone, for the great presentations. A big thank you as well to all of you who attended this workshop. So it was very nice to see many of you joining us. I hope you enjoyed this first edition of the workshop. And yes, again, don't hesitate to let us know if you have any feedback. And last but not least, I would like to thank the RecSys chairs and organizer for making this event possible, and also for being so helpful and available. So that's it from us. Thanks again, everyone, for joining, and well, have a great rest of your day or evening, depending on where you are, and have a nice weekend. Bye.
Thanks.